Hello, statistics student. This video is for chapter 11, the chi-square distribution. And for chi-square distribution, it is commonly used for something for chi-square tests, goodness of fit tests. If you Google chi-square, you'll see that it's used for those purposes. But in this particular course, we are studying something called test of independence that will use chi-square. Okay, what is chi-square? Chi-square is the name of a distribution that is right scale. So is you can think of in a normal distribution that is bell shaped, then the standard normal is a standard, right? So for a right scale distribution, chi-square is kind of like the standard. Now chi-square is right scale, that's what we say. But there is not just one. So there's not just one that just like that. So there's multiple of them, and their skewness actually uh, different by something called the degree of freedom. Again, if your sample size is n, degree of freedom is n minus 1. So if you have degree of freedom 2, your chi-square distribution is like really right scale. And then when the degree of freedom increase, it actually is getting more and more symmetrical. The peak actually move towards the center. And there's this statement in the book that say if the degree of freedom is greater than 90, the chi-square distribution approximated normal distribution. So this is some facts about the chi-square distribution. And you see that when I draw the chi-square distribution, they're all on the positive side of the x-axis. So because chi-square can only be positive. Chi-square has a peak around here, but that is not 0 or 1 because it's all positive. But what is this number? Is it 1? No, the mean is actually the degree of freedom n minus 1. And it's actually just located just right of the peak. So the peak is not n minus 1, but just around here, that is 24, you have the degree of 24. So you will expect to see not 0, 1, 2, 3. And you will see that because it's right scale, so your tick mark is not symmetrical. So it is very different. Just the x-axis is just whole numbers. So how do you calculate chi-square? What does chi-square shows up? Chi-square is sum of n minus 1 independent standard normal variables. So if you add sum of square, is it? I think sum of square. So if you have a standard normal z, you randomly pick a z. Oh, pick here 1.1, and then you square it, and then you randomly pick another square, another z. Maybe this time you get a negative number, z2 square, and somehow you add them together, you will have chi-square. So it is positive because you have standard normal that you randomly get, and they are independent, and they are positive. So if a chi-square is can be used to model something that is right scale, how do I find probability of a particular chi-square number? So there is a chi-square distribution calculator. We seldom use it, but I just want to show you actually so that you understand that it's actually just like a normal distribution. So the one that we use is from online stat book again because it's just easier to use. So what you do is you will give the chi-square number. So you can, like in a normal distribution, other time, in the other case, we have, we have a distribution, but here we don't. Okay, so you just have to put the chi-square number, the degree of freedom, and you will calculate the probability. So this particular probability is always greater than. Okay, so do an example. Because in chi-square test, we always use greater than. You only do greater than. Chi-square greater than that number. So for example, I want to find a probability that chi-square is greater than 31 when degree of freedom is 10. So if the degree of freedom is 10, so I would put 10 here. My chi-square number is greater than 31. Calculate 0.006. So the chance of having, oh no, the the degree of freedom. Yeah. Okay, so I should not write degree of freedom n equal to 10. I should say degree of freedom n minus 1. I think I should not say this. I should say n minus 1 equal to 10. Okay, because if you have n, so this means if you are my sample, I'm collecting 10 standard normal, 1, 2, 3. Okay, I randomly choose them. Sometimes they're 1, sometimes they're 3, sometimes they're 2, and I add them together, right? I square each one. So this maybe randomly I pick 1 is 0.7 square. And then this randomly I pick 3, I pick 2, 1.5 at 1.5 square. So it would be more than 10, right? Because, it could be negative, positive. Uh, um, you can have 2 or 3, right? So what is the chance that you pick 10? No, actually 11, right? Because degree of freedom is n minus u. 11 of these standard normal, and then the chance for the sum of the square to be greater than 31. So you would say chi square is greater than 31, and that is 0.0006. Okay, and then all of this number would show up as chi square, and your chi-square distribution is like this. This is 10, and then we want it to be over 31. 31 is here, and this area is 0.0006. So that's what the meaning of a chi-square distribution. So what is it used for? So going into 11.3 is used for testing of independence. In chapter 3, we learned that if someone gives you a contingency table that classify categorical data in two ways, this is one example. We classify people's favorite snack choice. Some people like chips if there's a choice. Some people like candy. Some people like ice cream if they have a choice. Between male and female. So what we want to do is, are they dependents? Are the choice affected by gender? Right. So if I don't look at the gender, like this particular table has total, right? So I have 108 people. How many percentage will choose chips? Versus if I just look at male, how many percent will choose chips? It does being a male affect the percentage of choosing chips? So that's what we want to do, is to check that if they are independence. And earlier when we do chapter 3, we also say, how do we check independence? Would be probability of A and B. You still remember? Is equal to probability of A times probability of B. If these are exactly equal, then they are independence. Now we can look back at this. Um, what is the chance that someone will choose chips out of total of 261? So you would do 108 over 261, right? 108 over 261. So out of the total, the people that choose chips is 41.3%. But if it is male, given that it's a male, so 40 out of 96 choose chips, which is very close, also 41.7%. So for chips and male, they seems to be really close. Although they're not exactly the same, there seems to be independence, right? Whether you are male or not doesn't affect your choice of choosing chips. Now, so that's what we say for particular A and B. What if I actually want to study all of them together? Does every single one are dependence or independence? So maybe this is not dependent, but maybe fruit is. Okay, so let's look at, out of the total 261, it disregard gender, 29. Okay, 29 out of 261 is 11.1%. But 9 out of 96 is for male is 9%. So there seems to be a difference. So it seems to be, if you don't look at the gender, there's a higher percentage of choosing fruits. But for male, if you know that that person is a male, there's only 9%. So take everything into consideration. Are there dependents? See the difference. And also when we do the chi-square test, they also take into consideration of whether of the sampling error. So like this case of 41.7 to 41.3, we would do a hypothesis test, and they would always look at sampling differences. So if there are actually a little difference, it would still be regarded as the same. Okay, so the way to do this is not to compare the percentage one by one. The actual calculation is they will do something called expected count. Expected count. So behind the scenes, or actually in the past, before you do the hypothesis test, what you do is you will build another table that show the expected count. That means if you just ignore the gender, using 108 being the total out of 261, how many, and using the distribution of male and female, how many will choose chips? The expected one when they are independent. And then you will calculate the x square, the chi-square would be equal to observed, this is the sample observation, minus expected count, square them, and divided by the expected count. Add them all together, they would become a chi-square, and then you look at chi-square greater than a value for calculating p-value. Okay, so in a way, that is how you do. And the chi-square distribution for testing these kind of tables would be, of course, you ignore the total column and row, right? So it would be the degree of freedom is r minus 1 times c minus 1, r being the number of row, c being the number of columns. So, so although we have 1, 2, 3, 4, we have 8 data, right? Ignoring the total. Yeah, 1, 2, 3, 8 number. So the degree freedom is not 8 because you do have 8 observed count and 8 expected count, but the degree of freedom is you minus the number of row, which is 1, you minus number of column by 1, so it's 3. 3 times 1 is 3. Okay, so that's how you do. We can talk briefly about this. So what is a test of independence about is to compare expected count with observed count in the contingency table to determine association or independence. Now, I want to also verify the test itself is independence. Independence means no association. Like gender does not affect your choice of snack. They don't affect each other. There's no association. It's called independence. If there is association, it's called dependence. Okay. So I think the one that we just look at in this table is they seems like they are independent because the numbers are really close, 9%, 11%. Although they're different, but it could be due to sampling variation, right? So let's go through the requirement and the steps, and then in the next video we'll do an example. The requirement to test this is the expected count in each cell must be at least 5 because all these x number of success are actually binomial, and in order for them to be normal, well, actually you see how the way we define chi-square is sum of squares of standard normal. It must be normal, so the expected count needs to be all at least 5. Of course, your sample is random sample, and the count that you have frequency counts. Okay, you cannot like build a tables of value and then start to do contingency table tests. Okay, when you do the hypothesis test, which is called chi-square test of the independence, you're always looking at the right tail test. Okay, so if you have a small chi-square value, the chi-square is here, then your p-value is very big. If you have a large p-value, large chi-square value, like the one that we have earlier, where n is 10 and then chi-square is 31, then you have more small p-values. Small p-value means the small p-value corresponds to large chi-square value. That means O and E are far apart. The observed and the expected does not agree. If your chi-square is small, your O and E are very close to each other, so you only have very small chi-square value resulting in large p-value. And you can see that although we don't say it, the chi-square tests of independence are right tail tests. Okay, so we'll do an example in the next video.